Welcome to qnawire.
Welcome to problem number 10.90. So this is chapter 10, dynamics of rotational motion. So here we have a flywheel which has a radius capital R 0.166 meter, and a constant force is applied in A part. So we have two parts here, so A and B and C. A part has given that force is constantly applied, which is equals to 25 Newton, and this cord moves 8.35 meter distance downward in 2 seconds. Initially, the flywheel was not moving, so after applying the force, the flywheel moves this way with omega angular velocity, and this cord, the end point, moves 8.35 distance. So this goes down, and this is d distance. So it takes 2 seconds. So we are asked to find out the moment of inertia. So first we will find out the moment of inertia for A part, then we will go to the B and C part. Here we have three formulas here. So we know that kinetic energy due to rotational motion is equals to half I omega square, and V equals to R omega, and work done is the integral of the force with respect to distance. So in first case we have constant force, that means work done is equals to F dot distance, because force is constant, which is 25 newtons. So 25 times 8.35 is the work done. Now this work done has been converted into rotational kinetic energy. There is no other kinetic energy, and we have conservation of energy. So we have work done equals to rotational kinetic energy, so which is equals to 25 times 8.35 equals to half I omega square, and we need to find this I here, but we don't know the omega, so we can replace omega, and we have another formula which is torque equals to I alpha, and torque is equals to R cross F. So in this case, we have torque equals to Rf, which is equals to I alpha, and we have another formula which is equals to omega equals to omega naught plus alpha t. Initial angular velocity, this is final angular velocity, and alpha is angular acceleration, and t is time taken. So here we have this quantity. So we find out the alpha. So this gives us alpha equals to Rf over I, and omega naught is equals to 0. So we have omega over t. Yeah, so omega equals to alpha t. So we have this equation and this equation. So we put omega equals to here. So this is equals to 25 times 8.35 half I alpha square t square. So we have this equation. Now we put alpha back here. So we have 25 times 8.35, which is equals to f dot d. Let's keep these terms into the in terms of the fd. So we have fd equals to, so this is fd, right? We came from this situation. So let's keep this fd because we will cancel down the factor. So equals to half I. Now putting the value of the alpha here, so alpha is rf over I, so rf over I square times t square, which is this. So this gives us I equals to f r square t square over 2t. Now we know the value of the f, which is 25 Newton. We know r, which is 0.166 meter, and we know time, which is 2 seconds, and we know d, which is 8.35. Now putting all these variables into here, so we get I equals to 0.165 kg meter square. So that's your answer for part A. We are done with the part A. Now going to the part B. So we have this graph. So in this graph we have force versus distance. You have to look at the graph very carefully. So in this situation we are given that this graph has value 60 here, and this is at 3, this is 2, and this is 6, and somewhere is 4 between them. So work done is equals to F dot dx. That means the surf is the area under the curve, under the FD curve. So we have to find the whole area of this. So we have area equals to, first we have this area, which is rectangle, so 60 times 3, plus this is a triangle having base 2, having height 60. So we have half into base into height. So this is our base. So we have this much work done. Sorry, this is our 3. Yeah, this is our 3. So this is our 3. So we should put 3 here. So work done is equals to 270 joule, and due to the conservation of energy, so this must be the kinetic energy or rotational kinetic energy. So that's your answer for part B. Now we go to the part C. So we are done with the I. We have find I. We have find out the kinetic energy. Now we find out the omega here. So we have at D equals to 6 meter, and using this force versus distance, we need to find out the omega at this distance. So we have K kinetic energy equals to half I omega square, so which is equals to 270 joule. So we have omega equals to root under 270 times I, sorry, times 2 over I. Now putting the value of the I here, so we have I is equals to 0.165. So this comes out to be 57.2 radian per second. But we are asked to find out the omega in revolutions per minute. So we have 1 revolution per minute equals to 2 pi over 60 radian per second. So 1 radian per second is equals to 60 over 2 pi revolutions per minute. So we use this conversion here. So we have omega equals to 57.2 times 60 over 2 pi. So this gives us revolutions per minute. So this comes out to be 546 rpm. So that's your answer for this question for your C part. Thank you for watching the video.